Okay, so you can see all these need a calculator, which you won't, on the AP test you won't have problems that need a calculator. So we won't worry about the calculator parts of these problems. And I think it's just this first one. Okay, so a cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. The can is initially empty and rain enters the can during a 60-day period. The height of water in the can is modeled by a function s, where s of t is measured in millimeters and t is measured in days between 0 and 60. Okay, the rate at which the height of the water is rising in the can is given by this differential equation, or the derivative of s. Okay, during the same 60-day period, rain in Monsoon Mountain accumulates in an identical can to the one in Stormville. The height of the water in the can. Did I get? Oh, whoops. Did I have? Oh no. Okay. Sorry. The height of the water in the can on Monsoon Mountain is modeled by the function m, where m equals that. Okay, the height m of t is measured in millimeters, and t is measured in days between 0 and 60. Okay. Okay, now it tells you that some function d is m prime of t minus s prime of t. And they say apply the intermediate value theorem to the function d on this interval to justify that there exists a time t, and it should say at which d of t equals 0. Okay, so in order to show that there's a time when a function equals 0, you always want to show that there's some point where on the interval where the function's positive and then some point where it's negative. And just to kind of remind people, so if you can find a single point where it's positive and then another point where it's negative, then if this is a continuous function, you have to say the function's continuous also. If it's a continuous function, somewhere it has to get to the next point, so it has to cross the x-axis somewhere in the interval. Maybe it crosses sooner, but somewhere on the interval to get from the top point to the bottom point, or the other way around, it has to cross the x-axis. Okay, so we just have to show that the function's positive at some point and negative at some point on the interval. Okay, so our functions are given by, here's our functions here. This one is a t, and here's m of t. Yeah, actually this is m of t, and this is s prime. So this is definitely just just doing this in the calculator. You could take the derivative of this, and you could do it in the calculator, at least graph it, and then figure out a point, maybe 0 and 60 you might try. So plug in 0 into the derivative of this, and then just plug in 0 into this, right? And then subtract them, like they say. And then do the same thing maybe with 60. Plug 60 into the derivative, and then plug 60 into s of t, and then subtract them again, and then one will be positive, one will be negative, and then by the intermediate value theorem, since this function d is continuous, then there has to be a point where the function equals 0. Okay, so I'm not going to write that. A lot of that would be in the calculator. So. Okay, according to the model, what's the average rate of change in the height of water in the can over the 60-day period? Show the computations that lead to your answer. Okay, so this one you can technically do two ways. If you get, the typical way is if you're given a function and you want the average rate of change of that function, like in this case we have s of t, and this represents the height of the water in the can. Okay, and since if we want the average rate of change of this function on the interval, then we'd have to do s of 60 minus s of 0 over 60 minus 0. Okay, so that's average rate of change, just slope formula on the interval. So you could do that. The problem is that we're not given s, we're given s prime. You could do this still. You could integrate s, and then the initial condition is you would use is s of 0 equals 0, right? Because it says initially, so when t equals 0, the height of the can is 0, so it's empty. So you could do that. Also, we have another option though. If we want to find the average rate of change of the height, we have a function that represents the rate of change of the height. This derivative represents the rate of change of the height. So you could just find the average value of this function on the interval. So the other way to do it is you could just do that average value formula. Like that. And I think this is the way, this would be the best way to do it, because if this was a calculator problem, you could just enter this into the calculator and that'd be it. So okay, okay, and this you could do either way, and that would just be a calculator problem. Okay, next one. Assuming no evaporation occurs, at what rate is the volume of the water in the can changing at time t equals 7? Okay, so if we want to know at what rate the volume's changing, then we need a formula that represents volume. Okay, so the radius, you can see here, the radius is 10 millimeters. Okay, so now we can use the volume of a cylinder, a can, is pi r squared h. Okay, we know that the radius is 10, so this is really, if the radius is 10, that's 10 squared is 100, so this is really 100 pi h, like that. And we know h is changing according to the function. Okay, so we can take the derivative of both sides with respect to t, so like dv dt. Okay, but then dh dt, the rate of change of the height with respect to time, is really just s prime of t. It's the same thing. Like that. Okay, and then we can just plug in 7 into this. And that's it. And then that we'd need a calculator for again. So make sure. Okay, and then the last one, according to the model, what's the height of the water in the can at the end of the 60-day period? Okay, so that's what these integrals were made for, to figure out, and this is like an important concept that I think that they're going to test for. So like or they could test for. So I think, or keep in mind, so like if you want to know the change in height of the water, then you can do an integral from 0 to 60 of just s prime of t, and that's it, right? So this function here is the rate of change, but remember when you take the integral of a derivative, it like those cancel out. Those are almost like inverse operations. So here, if we take the integral of this rate, we'll just get height, you know, and this will really be the change in height. And that's what we want. If we want to know what the height is, we want to know how much it changed. And then we can add it to the initial height, but this initial height is 0 since it starts out empty. So whatever this ends up being, this would just be the answer. And if you do it in a calculator, it ends up being 602.218 cubic millimeters per day. Okay, and actually this one here, I'll give this in case anyone did it, ended up being, oh no, sorry, I made a mistake. This one goes up here. And then here, sorry. Yeah, 3 was that. 4 ends up being this. 171. And then here, let me get number 2. Ends up being 2.863. And that's millimeters per day. Okay, and then here, what was number 1? Oh. Yeah, and just so you know, for number 1, if you actually end up doing it out, d of 0 was negative, should be negative, and d of 60 should be positive. So, okay, that's everything. All right, this one gives a graph of f, and it tells you the continuous function f is defined on the closed interval from -5 to 5. The graph of f consists of a parabola and 2 line segments as shown in the figure. Let g be a function such that g prime equals f. Okay, fill in the missing entries in the table below to describe the behavior of f prime and f double prime. Okay, indicate positive, negative, 0, give reasons for your answers. Okay. Okay, so we're given the actual graph of f. So f prime is going to be positive whenever f is increasing and negative whenever f is decreasing. Okay, so from -5 to -3, it's increasing the whole time. So this will be positive. Okay, so from -3 to 1, it's decreasing the whole time. So it'll be negative. From -1 to 2, it's increasing, and then from 2 to 5, it's decreasing. So positive, negative. Okay, second derivative is concavity. So between, so on this region, here, sorry, oops. On this, from -3 to 2, this is concave up the whole time. So the second derivative will be positive on that interval. So these will both be positive. Okay, and then on the outside where these are linear functions here, those don't have concavity. Linear functions, there's no curvature, so there's no concavity. You can also think if you took the second derivative of linear functions, they'd always be 0. And so that's what these are. These are 0. Okay. Okay, and then for part B, so there's no value of x on the open interval from -1 to 5 at which the derivative equals, and then do you see this is the slope of the secant line on this interval. Okay, but they say there's no value of x on this interval at which the derivative equals the slope of the secant line. So the mean value theorem says that there is a point on an interval. There's always a point on an open interval where there's a point where the slope of the tangent line equals the slope of the secant line, where the derivative equals this slope. And so, there should be, according to mean value theorem, but this says there's not. So they say explain why this doesn't violate the mean value theorem. Okay, and it doesn't violate it because the mean value theorem, in order to be able to apply it, the function has to be continuous and differentiable. It has to be continuous on the closed interval and differentiable on the open interval. But then you can see from -1, if you look on this interval from -1 to 5, it's not differentiable when x equals 2. And so you could put that since f is not differentiable, when x equals 2, then the mean value theorem does not apply, and so is not violated. Something like that. So, a bunch of different ways to say that, I think. Okay, for part C, it says find all values x at which the graph, or on the whole interval from -5 to 5, at which the graph of g has a point of inflection. Okay, always start, try to be good about working backwards. So if you want a point of inflection, you need second derivative, right? And you want to do second derivative, find critical values, put those on a number line for the second derivative, and see if it changes signs across the critical values. If it changes sign, it's an inflection point. If it doesn't change sign, then it's not an inflection point. Or if it's not defined in the original, then it's not an inflection point. Okay, so doesn't matter. I know this is g is defined in terms of f, but doesn't matter. So we're still just looking at the second derivative of g. So they give us g prime equals f, which means g double prime is f prime. Okay, so if we want to know where g double prime is either undefined or 0, we really want to know where f prime is either undefined or 0, since they're equal. So we go to the graph. Okay, so it's undefined f prime, the derivative of f is undefined at 3 and up here, at -3 and 2. And then it's 0 at -1, right? This slope is 0, so f prime is 0. So there's 3 different x values. So at x equals, oh, but we still have to do a number line here, sorry. Okay, so we'll put those values on there. So what were they? -3, -1, 2. Okay, we'll do test points. Oh no, we won't do test points. We just look at the graph. Okay, so that's where the it's where f prime is either 0 or undefined at these values. So now we have to see where f prime is either positive or negative. So from -5 to -3, this is positive since it's increasing. From -3 to -1, it's negative. It's decreasing. And then it's positive and negative. Just looking at increasing and decreasing. Okay, and so those are all inflection points. So that we have inflection points at x equals -3 and 2. Okay, and I'm going to say because f prime, which equals g double prime, is undefined and changes sign. And then at x equals -1, because prime g double prime equals 0 and changes sign. Okay, something like that. Okay, next one. At what value of x does g attain an absolute maximum on the closed interval? Give your reason for your answer. Okay. So anytime you want to find absolute maximum on a closed or on an interval, you do the same thing every time. So no number line for this. Okay, so when you want to find absolute maximum on an interval, you find all the critical values and then plug the critical values and the endpoints of the interval back into the original function, and then see which one's the biggest or smallest, whether you want to max or min. Okay, so we want to find all the critical values of g. Okay, so keep in mind g prime equals f. So critical values of g are where g prime is either 0 or undefined. So really it's where f is either 0 or undefined. So we go up here. And so you can see f is never undefined. The derivative of f is undefined at certain places, but f itself, this function, is never undefined. And this is only 0 at the endpoints. Okay? And then keep in mind, so if we look at it, g prime, which is f, is always positive, right? This is the graph of g prime, and g prime is always positive, which means g is always increasing. So there's no critical values, but we can say since g prime is always positive, at least on this interval, then the regular function g of x is always increasing. And hopefully it makes sense. If a function is always increasing on an interval, then the right hand side, the right endpoint, will always be the maximum, right? If you have a function that's increasing on some interval, this will always, the right hand side will always be the maximum because it's increasing, like to get to that largest point. So we can say since g prime of x is always positive on the interval, that means g is always increasing. Therefore, g will have a max at x equals 5. Okay, and that's it for that one. All right, next one, cylindrical barrel with a diameter of 2 feet. Okay, so that means the radius here is just 1 foot. Mark that. Okay, contains collected rainwater as shown in the figure above. The water drains out through some valve not shown at the bottom of the barrel. The rate of change of the height of the water in the barrel with respect to time is modeled by that equation, dH dt equals negative 1/10 square root of h, where h is measured in feet and t is measured in seconds. Okay, the volume V of a cylinder with radius r and height h is V equals pi r squared h. Okay, find the rate of change of volume of water in the barrel with respect to time when the height of the water is 4 feet. Okay, so this is like a related rate question. So we want to find dV dt, rate of change of the volume with respect to time. Okay, so we'll start out with our volume equation. Okay, we realize plug in, before you take the derivative, you can plug in anything that's not changing. So we can see this, the radius isn't changing, and it's 1 foot. So we can rewrite this as just pi h. Since r is 1, r squared will be 1, and that'll go away. So now if we take derivative, dV dt is just pi times dH dt. Okay, and then they give us dH dt, so we can plug that in, substitute that. So it's negative 1/10 square root of h. Okay, and then we want dV dt when the height is 4 feet, so we'll just plug in 4 for the height, and we get negative, okay, if height is 4, the square root of 4 is 2, times 1/10 is 1/5, so this would be negative pi over 5. And then units will be dV dt, so change in volume with respect to time. So this will be cubic feet per second. T is measured in seconds. Okay, next one. Okay, when the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? Explain your answer. Okay, so they want to know when h is 3. Change the height of the water with respect to time. Okay. They just want to know, yeah, when h is 3, is dH dt positive or negative? So here, if it was increasing, dH dt would be positive. If it's decreasing, dH dt would be negative. Okay, so we have a formula for dH dt, and we can see when h, actually, since h is always positive and the square root's always positive, that means dH dt is always negative. Oops, what am I doing? Okay, yeah, since this is always positive, dH dt is always negative. Um, Therefore, dH dt is always negative, is always decreasing. And so is decreasing when the height of water, when h equals 3 feet. I don't know, something like that. Okay, last one. At time t equals 0 seconds, the height of the water is 5 feet. Okay, so that means like h of 0 is 5. Okay, use separation of variables to find an expression for h in terms of t. Okay. Okay, so let's do that. So we'll take that differential equation, dH dt equals, and this will be, I'll rewrite this as h to the 1/2, like that. Okay, so they say use separation of variables, so we'll get all the h's together on the left and the t's together on the right. So basically we'll divide by h to the 1/2, and that'll really end up being h to the negative 1/2. And then we'll multiply by dt to bring it over here. This will be negative 1/10 dt. Okay, so now we separated the variables. The h's are on, oh, wait, whoops, what am I doing? No more dt once we multiply it. Okay. Okay, and then now we got the h's on one side and the t's on the other. So now we can integrate both sides. Okay, integral the left-hand side, 2h to the 1/2, right-hand side, and we'll have that plus c. All right, to find c, we'll plug in our initial condition, t is 0 when h is 5. And I'll turn this back into a square root, maybe. Okay, this just goes to 0, so that means c equals 2√5. Okay, so we can plug this back in to there. Okay, and then they say use separation to find an expression for h in terms of t. So we have to still solve this for h to get h by itself. All right, so we got to get rid of the 2, so we'll divide everything by 2. These 2's just cancel. And then if we divide this by 2, this will be 1/20. So negative 1/20 t plus √5. And then now we could just square both sides. And that's it. That. Okay, and that was everything.